So a couple months ago, we started to think about the topic for this year's Analytics Center events. And we come up with these ideas of energy and AI, and suddenly we realized the entire world was talking about it. Elon Musk was talking about transformer for transformer. Jensen Huang is talking about we need more energy for computing. So we really hit the right topic. And then really, computing and sustainability is a full stack challenge. We need innovations from the transistor level. How do we make these chips? How do we power it? How do we build the data center? And there are also challenges on the grid side and the regulation, policy, and economic side. So that's why how we set up today's panel discussion. So we'll start from the very bottom. We'll hear about from Professor David Wentzlaff and his panel on where's computing heading towards. Are there better ways that we can build computers so that they can support our future computing needs? And then we'll flip the coin. We'll start from the top. Professor Jesse Jenkins, who is an expert in energy system modeling, will talk about policies and how do we get power from the grid, and how does utilities are thinking about to meet this challenge of powering future computing. And then we'll have a lunch break. And after the lunch break is about 2 hours. It'll be happening in the Frisk lab, about 10 minutes walk from here. So you can walk around the campus and enjoy the fall leaves. And then we'll come back from lunch, and then we'll flip the coin again. And I'll be leading a panel talking about how do we use AI to advance energy systems. How do we make energy systems more sustainable? And finally, we'll have a last session closing our today's session, which is AI for climate. How do we build artificial intelligence models to model the climate system and enhance our understanding about the Earth and the sustainability. So without too much delay, I'll hand the panel to Professor David Wentzlaff, who built large-scale computing chips in his lab.
Thank you. Thank you. So the plan for today's panel, how we're going to run it is we're going to have 4 panelists and myself moderating it. And each of the panelists is going to give a little bit of insight about their research and view on what computer architecture and what computing is going to look like under the with AI and sort of how energy and AI work together here. And just to give a little bit of background on our speakers, so I want to invite them up here. Can we have Tom Gray? Come up and have a seat. Tom is a senior director of circuit research at Nvidia, and he leads activities related to high-speed electrical signaling, photonics, power delivery, security circuits, low energy and resilient memories, circuits for machine learning, and variant tolerant and clocking and power delivery. Next, I want to have Professor Mark Johnson come up. Mark is at Clemson, and he is the director for the Center for Advanced Manufacturing, and he's the Thomas F. Hash Endowed Chair in Sustainable Development in the Department of Materials Science and Engineering. And he's also a professor in the Department of Materials Science and Engineering. And his work looks at clean energy and technology, and particularly in sort of the manufacturing side of the world, and how to go build environmentally friendly materials. Next, I want to bring up Stephen Kosonocky. Stephen is a senior fellow design engineer at AMD, and he leads the he leads the low power advanced development team, and he focuses on low power circuits. And then finally, I want to bring up Dr. Carole-Jean Wu, who is a director of AI research at Meta, and she leads the systems and machine learning research team, and she's a founding member and VP of ML Commons. And her research is at the intersection of computer architecture and machine learning, and has done significant work in sustainable computing also. Just a little bit of background about myself. I'm a computer architect, and my research group primarily has been looking at, most recently, how to go build computer architectures for large language models. And we've also in the past looked at computer architecture at the end of Moore's Law and sustainable electronics. So to give a little bit of background on sort of where this panel is going to go and what we're thinking about, and what we've been thinking about in our preparation calls for this talk. I just want to give a little bit of background of sort of where computing has been going, where computing will be going. So this is a pretty wide audience. So as you may know, there is this little thing called Moore's Law. So Moore's Law is the sort of continuing Moore said in a 1965 electronics article that sort of computing is going to become cheaper and cheaper exponentially with time. We are now in sort of a little bit of a crisis in computing. We've seen Moore's Law slow, and it's not just like feature size shrinking and that slowing down, but it's also just the cost aspect has been shrinking, slowing down. So I sort of wanted to set the stage here that the fundamental thing that's been driving a lot of the advancements in reducing energy for computing has stalled a little bit. So this is something that the computing industry has been thinking very, very hard at, and we've all been trying to save energy to the most, but it gets difficult. Together with Moore's Law is something called Dennard scaling, which is basically the reduction in voltage, which was sort of directly driven to the reduction of energy, and that stalled a long time ago. So we are sort of at a little bit of a crossroads here, and I just want to sort of set that stage here for those of you who are not necessarily from a electrical engineering background. Now I want to actually bring up our first speaker who's going to talk a little bit about, our first panelist is going to talk a little bit about his view of where AI and computing is going here. So leave it here to Tom.
All right, thank you, Dave. Okay, yeah, thank you for the intro here. Really important topic, great keynote here this morning. We're taking a dive really to the other end of the spectrum here, looking at circuits and the implementation of these types of systems. The plot here on the right side of the screen is probably why most of us in one way, shape, or form are here today, because if we look at the amount of petaflops that are being consumed in these types of AI networks, we're on a steep curve on a log plot here, right? And if anything, it's becoming steeper as we go ahead, and I haven't even plotted the latest data here. So there's a sort of insatiable amount appetite for compute for these types of applications, and then at every step, every part of the hierarchy, we're limited by energy or power. So basically, down at the die level, we're constrained. At the rack level, we're constrained. In the data center, we're constrained. And then we've talked about the global view this morning already. So how do you address something that's increasing at that kind of on that kind of an exponential? And so the way that we've done this over the past eight or so years at the module level or at the device processor GPU level is shown here on this graph. And it hasn't come by only in only one area. There's been something like 1,000x increase in compute ability, performance over these 8 years, which is amazing, for anything over a time period like that. Dave mentioned Moore's Law. Moore's Law process change has given us some benefit, but you can kind of see it's like the third one down there at maybe 2.5x of that 1,000x. So obviously, this has come from other things, and that it's taken architecture changes, it's taking number formats, it's taken dedicated hardware, and it's taken optimization of the actual networks themselves. And there's still a lot more to be done here, right? So we've gotten that 1,000x over the last 8 years. What do we do going forward? So what does that cost, though? This is the left side plot here is taking that same data that was on the previous slide, plotting it on a log scale, and then plotting on top of that the energy that is used or the power that's used for the processors themselves, sort of at the die or few die kind of level. And you can see that the power used at the module level is going up, but it's gone up at about a 3x change over that time period where we've gotten a 1000x improvement in performance. So while that 3x change at the module level is a lot of stress for people like me who are dealing with the devices at the bottom level, it kind of shows us hope that we can get to where we need to be on these exponential curves without, such a huge increase in power at the device level. Now, of course, we're getting a lot of that benefit by expanding out into many more data centers, as was talked about today, and the data centers are springing up. But at the module level, we've kept it somewhat contained. So where are we going? These are the kinds of things that that our group kind of concentrates on here. And if we look at the amount of power that's being dissipated at the module level, much of that comes from interconnect, just moving bits around. It can be anywhere from a third to a half of the module power, just moving bits around. And so because of that, you see systems that are collapsing. We're building 2.5 3D type systems that minimize the capacitance of the interconnect there so that we can do more efficient interconnect between the different parts of the devices. But that causes a lot of stress on both the power delivery system for the module as well as the cooling system for the module. And so a lot of our work is concentrated on that. Cooling at the top, advanced substrates at the bottom, power delivery up through the stack, minimizing electrical communication inside the stack, and then photonics for low power outside of the module. This is not an Nvidia product plan here, but more of a concept of where we see things going here. So these modules will keep increasing. The power for those modules will keep increasing, but we're doing all that we can to contain that and optimize the amount of performance that we get out of the system, given the amount of power and amount of cooling that we can sustain here. So, all right.
Thank you, Tom. So I'm Mark Johnson. I think this will end up switching the slide. I'm with Clemson University. Previously, I was actually spent an earlier part of my career, say the first half was actually a semiconductor materials and device researcher that through a weird twist of fate, doing work with DARPA, wound up having me help launch a place called ARPA-E at DOE, and then was the director of advanced manufacturing. So I sit in a position that's kind of a unique position where I've lived the world in the semiconductor innovation and I've lived the world in energy and big energy systems. So where is this going? And the bottom line on this, and you look at AI in the title here, I actually am expanding it, looking a little bit more comprehensively, and say just the information technology sector overall, whether it's telecommunications, data storage, AI, wherever it is, the question we have to ask is how much energy is being used by the information sector overall. And early in the days of the internet, there were a number of studies done in like the 1990s where the immediate thing that happened when the internet came out saying, oh, this is expanding exponentially, it's going to consume all the energy of the planet. A number of studies came back, and that was some of the early studies of how much energy is being used by the information sector. Their takeaway was, we're 5 orders of magnitude away from any problem there. Don't worry about it. You're not going to need to build power plants in 1998 just because, Alta Vista is going to wind up taking over things. Sorry, I'm showing my age there. But, the world changes. But we do have this underlying Moore's Law question. And one of the corollaries to Moore's Law is that you're getting more efficient, and it's actually not efficiency, it's information productivity. You're getting more information data processing capability per unit energy in every Moore's Law cycle. So the race we're in is as you double that productivity, that energy efficiency in your computational process, which the semiconductor community and the device community is doing a remarkable job for 50 years to continue driving down that. We are running into some headwinds on it, but it keeps driving down that. If when we wind up doubling that information productivity, if as a result the number of applications grows, So we actually increase the total computational applications that are used as a result of that. We actually grow the total energy used. And that's the race we're in. So the question is, where's the data? And you'll see the data is actually pretty sketchy. But at the end of the day, global energy generation capacity, electric energy, by the way, because we're talking about electricity and electrons, grows somewhere around 2% a year, about 1.5% in the United States generation capacity, and more than that in developing economies. So that's a good thing. But that's the growth rate they're talking about of overall electric generation capacity. If you look at energy use in the information sector, it's growing anywhere between 10% and 15 to 20%, depending on whose data you look at. Again, this is going to be one of my themes. We need better data on this and primary data. At some point, those two things wind up intersecting. That's probably going to wind up happening in the lifetime of every student that's in this room. So what's going to wind up giving on that? That's the question. So here's my attempt at looking at the data on it. And some of the studies in the 1990s, as I said, are over on the left. You've got some of the more recent studies and projections that are looking at it. And the takeaway here isn't to say what year are we going to wind up running out of electricity, because that's not what's going to wind up happening. But we're getting increasing pressure and demand on the use of electricity by the information sector. And that's going to fundamentally change the economy that's happening. Now, this isn't the first time people have looked at this. This is from, I think it was the IDM review paper or IDM invited talk that Gordon Moore gave in 1995 on the 30th anniversary of Moore's Law, and looking at how fast is the semiconductor industry growing. And his projection, his extrapolation was sometime in the late 2040s, the semiconductor industry's GDP would be higher than the world GDP as a result. So that was very futuristic then. It's less than 20 years from now. So what does that mean? You always have things when you have crossovers having renormalization that happens. But the real question here is we wind up having generation capacity wind up expanding, right? So the problem we have is not just the generation capacity. This isn't exactly the time horizon where the planet's going through this climate crisis. 2050 is the Paris Climate Agreement target dates we're looking at. If we don't do something about this, this becomes really, really problematic. Done well, however, because there is a high economic value add, the information technology sector can wind up actually facilitating a faster transformation to clean technologies. Done poorly, it will actually wind up locking in CO2 emissions the way we are right now. And that's the race we're at, right, that we're looking at. So one of the challenges you also have is there's literally no human activity in conversion of electricity to something of economic value, of higher value than the information technology sector. We literally in cryptocurrency are turning electric energy into money. There's no other activity, that steel making, electrifying it, any other electrification process does not do that. What that means is that the information technology sector is the ultimate base load, meaning you are going to shut everything else off on your economy if you're an economic actor on this. Or what you're more likely going to do is raise the prices, because that's how you allocate that asset, of everything else before you wind up abating the use of information technology sector. So the idea that somehow you're going to wind up using data farms as balancing reserves to balance renewables is kind of idealistic thinking on that. That's my opinion. I think this is an area we need more studies on. So how do we wind up doing that? That's our challenge. So here's the good news. For those of you who are in the IT sector and not deep into generation capacities, there's a bank, Lazard, that does a study every year on something called the levelized cost of electricity or levelized cost of energy. This is the cost because you've got CapEx and OpEx and all these sort of fuel costs and things like that give you a head-to-head comparison economically of what's the cost of expanding generation capacity, because we are going to need to expand generation capacity to meet that 10% growth curve. So start out with, we're going to have to go up by 5x the amount of generation capacity we're creating on the globe to match that. A huge transformations happen from the upper left to the lower right. That orange curve is solar. So the idea that, first of all, nuclear is the lowest cost energy resource on the planet is no longer viable. The other is that coal was somehow put out of business because of some big conspiracy that went on. No, natural gas prices wound up coming down. So the order of the costs of generation capacity are solar, wind, onshore wind, offshore is coming down, but then combined cycle natural gas. Natural gas is something called dispatchable. You can turn it on and turn it off, where wind and solar are not. So we need storage that winds up coming into it. The good news, these are coming down in prices. This is, by the way, a picture of it was actually an oil burning plant, I think, down in Toms River, New Jersey, that came down because it was no longer in the money to run a coal-fired power plant or a fossil fuel power plant because of the displacement of other resources. Mostly natural gas is what put the coal industry out of business. It was literally more valuable to use the real estate and redevelop it than it was to keep making electricity out of that land. So, that's the pathway we're on. The concern you have, and you're already seeing this in the cryptocurrency business, people then extending the lifetime of things like coal-fired power plants because you can turn that into something of economic value. We've got a problem there. We need to wind up having a cost or a price on coal as a result, or on carbon. By the way, I grew up in the power industry. My father actually worked for what's now Xcel Energy, and he worked in the coal-fired power plant industry until the day he died. He said, we need to have solar, we need to have fusion. So here's my recommendations. My first recommendation we can have, one is we need better information. The Energy Information Agency of the US government does not track energy attributed to the information sector on an ongoing basis in their annual energy outlook. They need to start doing that because without data, we can't manage things. That's the first thing. Second is we actually need to price on carbon. Since we're speaking here at Princeton, this is George Shultz's favorite thing in policy recommendation. So I fully endorse that. We need to get there. And we need to continue to invest in the technologies. Thank you.
Hey, good morning. My name is Stephen Kosonocky, and I'm happy to be invited here. I actually grew up about 5 miles north of here, so I'm a native here, New Jersey, and I started my journey in power efficient computing about 25 years ago when I was at IBM Research, and since then, we were kind of looking at what was going on and how to empower and power efficiency for the data centers. Let's see, I think it's. Yeah. And a few years ago, I was part of a work group from SRC, or Semiconductor Research Center or Corporation. We were putting together a decadal plan for semiconductors, and I was part of. I co-authored one of the chapters on energy efficient computing, and we came up with this one chart here. This is actually was kind of spearheaded by one of the PIs there, Victor Zernoff, and he plotted out this interesting thing of the total compute energy per year in the world, and this includes cell phone, compute, everything. He just kind of calculated it all up and looked at the world's energy production, curves, and then plotted them, and you can see that similar to Mark's chart. We're on a kind of a collision course with the world's energy market, but there's certain market dynamics that will never let us actually cross over, right? Of course, because something's got to give. We're going to either bend or something's going to change. So there was a real new need for new trajectories for computing, for getting performance. You can't just add power and get performance. You need to do something different. So. As Mark pointed out in his presentation, or his slides, there is really an insatiable demand here for compute performance. And here is just really showing again, just the demand portion of this is just in terms of zeta instructions per second. I don't even know what a zeta is. It's a lot of zeros. There's a total world's performance. And you can see that again, there's something that's got to give here to kind of get us past this 1,000 zeta instructions per second max. That was kind of coming from the other slide. There's some sort of cap there, and something's got to give there to break that barrier there, or change the trajectory. So if you look at today's data centers power here, up to now, roughly, in 2020, this is a chart from Goldman Sachs from back in May this year, and you can see that the terawatt hours of the data centers here was actually not increasing up to 2020, where there was actually excess capacity there in terms of power. And then you can see that along on the left, the estimated total data center workload demand. So the demand was a little less than the power capacity there. And as it was coming up, and so there was, it stayed flat mainly because there was a lot of power efficiency improvements in data centers, and things that the different companies doing, AMD, Intel, Nvidia, and so forth, and Microsoft in data centers, they were figuring out how to deal with this power and keep it mostly capped. And like Mark said, on his is like, the performance going, or sorry, maybe it was Tom, the performance is going up much faster than the power was only going up like 3x. So but we're hitting that limit now. And then there's another plot here. It kind of says the same data, but it's kind of pointing out the total the components in the U.S. and the rest of the world here. And you can see that AI is still pretty small fraction, but it is increasing fast. So, it started about last year, 2023. We can see that, the AI component of the power is still relatively small, but is projected to be much higher as we go forward here. So there's another plot here. This is a plot from Bernie Meyerson from IBM. Bernie Meyerson is an IBM fellow. He's now retired. And this is looking at power density in computing and servers. And power density is is a good proxy for total power, really. And what it basically was showing is the transition from bipolar to CMOS, and really what drove that. I was at IBM in the mid-90s, actually, right there at the bottom when CMOS started. So I never worked on the bipolar stuff, but came in the second part. But you can see that the transition there, we had bipolar servers, way back from the 60s, and we started, water cooling them. We moved away from air cooling. They were very large, and we kept on that train as far as the industry could, to keep going to get performance, because performance was money. You just keep, demand there was coming. And then finally, IBM made that switch from bipolar to CMOS. And that was very controversial. They took a hit in performance there to make that transition, and because it was just unsustainable. I had some colleagues who used to work for IBM earlier than I did, and they were computer architects. And if they had an idea on a new kind of idea for improving performance, one of the directors would say, "Well, how much does it weigh?" Because there was a lot of boards, these things, were, big. We kind of laugh at that now because everything's so small. But back then, there were components. These are all discrete components. So anyway, so that went up. And then, then CMOS in the mid 2000s, got this similar power densities. There was a really good plot from Intel back in the ISSEC that was saying the same thing. We were just, at the power density of the computer of the sun. We're approaching that, and then the industry came in and solved these problems. First was multi-core scale out. You can't just keep scaling up the frequencies. We capped those around mid 2000s, 2005, and we stayed there in that level and went to multi-core. Figured out re-architected to get more performance. Our systems then took advantage of that and got the compilers pushing things out, getting multi-threads. Then came GPU compute, and about a decade later really came to play, where that was getting looked at for exascale and applications in supercomputing. Then again, we're running out of space on the die, so we went to multi-chip modules, mini chips, and then went to heterogeneous modules where you have many different types of technologies put together, so you get the best technology for the certain functions, for the memory, for the logic, so forth, for the I/O. And then, now we're getting to either tailored or domain-specific computing to really have targeted architectures that are most power efficient for the algorithms. And there's always a challenge there, and a good example there is look at like IBM's like True North or North Pole AI chips, those are very power efficient, but then they are very specific, so you're locked into the algorithm. So as AI is going forward and still developing the different algorithms, different software, they may be optimizable differently. So there's always kind of this back and forth there in what to do in the architectures to optimize it. So I'll leave some key challenges here. Really, there's ever rising energy demand for computing for global production. That's creating a risk there. The computing and data center power demand is relentlessly increasing. We don't see that ever stopping soon. Conventional power efficiency techniques will quickly run out of steam. I've been working on this for 25 years plus, and we're using everything we can to make it more power efficient. New computing paradigms and architectures with radically new computing trajectories are required, and that's key. When we look at all those things I mentioned, those are all new trajectories that are reducing the power and the energy consumption. And then again, new devices, circuits, systems, and architectures will be developed as these AI applications evolve and people understand how to optimize for them. So I'm very optimistic there. Come to solutions. Thanks.
Nice.
Hi. No. No? How about now? Okay, cool. Such a great honor to be here and share some of my thoughts about where AI is going and the energy and sustainability implications of this important technology. So we hear a lot about all the technology breakthrough on this panel already on how efficiencies is helping us to keep the energy consumption of computing intact. And this is a statistics that a science paper published not too long ago. The idea here is that when you look at the compute instances that has been installed into global data centers between 2010 and 2018, what we have found is that the number of compute instances has increased by 5.5 times, while the associated energy increase is only increased by 6%, 0.06 times. And all thanks to the efficiency breakthrough cutting across the entire hardware software ecosystem. But all at the same time, we have this new application drivers that's coming online. In fact, if you look at a green AI studies that I have charted out at Meta, at around 2020, 2021, we already see the amount of data that's trained, that's used to train the AI technologies at a company has doubled within less than a 2-year time frame. And all that data is used to figure out the parameters in the ever-increasing large model sizes. Within the same time frame, we see the amount of parameters in large deep learning models has increased by 20 times. And all that increasing model parameters and data volume for AI is translated directly into the amount of infrastructure that we put into data center infrastructures. Now, if you look at the sort of rise of ChatGPT, end of 2022, 2023, we start seeing a lot of projections on how this important technology is going to increase the energy use of data centers at scale. So on the figure on your right-hand side, we see various different scenario projections that shows how, given this significant AI technologies on the rise, what is the impact on energy consumptions at the data center scale? As what you heard from Dave's opening of this panel, Moore's law is slowing down quite a bit, and all the additional efficiency improvements at all scales, at data center scale, is also slowing down quite a bit. Today's data center is quite optimized with power usage effectiveness close to optimal at 1.1 today. That means that only 10% of energy is going to overhead in terms of cooling the data centers and all that. And so in this particular study, we see that the gray curve is showing the efficiency improvements going forward has slowed down quite a bit. But all at the same time, the amount of power demand of AI is driving the aggregated energy consumption overall. So you see similar data from some of the panelists earlier, and so I won't spend more time on this particular trend analysis. With that, I guess if you look into the publicly available sustainability report from all the big 4 hyperscaler companies, you will see the energy consumption of the 4 companies has been increasing at various different speed. And it is actually a good thing that companies are putting a lot of efforts into understanding, quantifying, and make these statistics available. Transparency does a lot of good for us to understand where compute cycle and energy is going. With the slowdown of efficiency benefits and with the significant growth in the application driver, what we are seeing is that larger computer chips are getting built, as what we heard from panelists from AMD and Nvidia. And also on the y-axis, we're seeing that more data centers are getting built, and these are increasing the public space land use at the same time. And this is also something that strongly supports the phenomenon called Evans paradox, which says that when the application demand is high, we are going, and when the cost is improving with efficiencies and all that, we should expect the aggregated resource consumption to continue going up. And AI is an important application driver here. If you look at where AI is going, this is a study that I have carried out to understand what is the operational energy footprint and carbon footprints of large models. We will see that across the past 4-year time frame, the amount of energy and corresponding carbon footprint using market-based methodology, the operational training cycles will increase quite a bit, and sometimes it's increasing super linearly with the latest generation of the foundation model, large language model called Llama. And going forward, this is only a part of the life cycle emissions. Operational carbon emission is only a part of the important life cycle. Going beyond operational energy use, there is this important factor that's becoming more dominant, which you hear from today's keynote speakers on the importance of embodied carbon. If we take Apple's sustainability report, we can see that across the Apple's company level carbon emission data, we see that about 74% of Apple's overall company emissions is coming from manufacturing emissions. And among that 74 manufacturing emissions, about 33% is coming from manufacturing of the integrated circuit, while only 19% is coming from product use phase. What this is telling us is that understanding where carbon emissions or environmental implications of computing devices is a very important first step in order to figure out what to optimize and what is the focus of reduction. Right? So going forward, in the very near future, we should have augmented reality wearables coming. And the operational and embodied carbon breakdown for these wearable devices are going to look very similar to what Apple has shown, with significant emissions coming from manufacturing and roughly 20% on operational emissions. But that doesn't mean that the story stops there. There are going to be all the additional data centers that need to be built in order to support this next wave of computing technology. And so going forward, I believe that there are 4 important areas that we must focus on. First, we must make AI efficient across the entire hardware software stack, as what we have talked about here. That's the bread and butter for computer system designer. But there's a lot more that we can do in the intersection between AI computing and sustainability. Second is that we should go figure out how to make AI computing a lot more flexible than it is today. Failure is going to happen. power grid is going to come with a different level of availability, especially for renewable or other clean energy sources. So how do we make our computing stack flexible to changing environment is a very important investment area. And also AI can be part of the solution, as what we'll learn later in this particular event. And then finally, a very important but underexplored territory is to understand and be able to quantify the manufacturing emissions of AI hardware. And with the tools that we have developed in my research group, we have go figure out how to quantify the embodied carbon, and that's the only first step. Now we are looking at the trade-off between operational embodied carbon at the hardware design. So this is a little bit about where I see our field going, and looking forward to more conversations here. Thanks.
Thank you, Carol. So we're going to have some time at the end for questions from the audience, but I wanted to kick it off our discussion here with some discussion points that we talked about a little bit, but I think it would lead to some really great discussions. So the first discussion point I want to lead off with here is, we've seen announcements that nuclear power is being rephased in to feed AI data centers and feed the sort of need of our computing. What is your vision for the future for computing and energy growth for AI? And will humanity's desire for AI and hence need for energy grow forever, unbounded? Or will there be some new technology, computing, AI algorithm, materials, energy markets that will disrupt this unbounded AI or generative AI growth?
Started with an easy one, right?
Yeah, I mean, it's cut right to the issue here. Are we going to grow forever? Or will we, I think you, Mark, you had said that there might be some economics reasons that we may not be able to grow for forever. But will there be something, or is this all doom and gloom? End of Moore's law is happening. We're not getting more efficient circuits. We can do a little bit more optimization.
Yeah, so I mean, I think one of the things that will wind up happening will be a huge driving force, let's start out with that, to increase the amount of generation capacity we have for the planet, right? So if you've got 2% growth rate and 10% growth rate, fine, I'll give only 5% growth rate, whatever it is that is the growth rate of total information technology usage. Something's got to give at some point. They're coming together. What typically will happen is you'll have a market response to begin with. You're already seeing that, the early stages of that, where people say, hey, we're going to restart 3 Mile Island. I think that's great that people are working on that. It is a completely non-scalable solution. Maybe we'll restart, I don't know, Chernobyl next or something. I don't know, whatever. But that's not a scale. I mean, it's great you're doing it, but it's not a scalable solution. I think we're going to have a massive increase in the amount of solar that's going to wind up happening. Massive increase in the amount of batteries that are happening. The concern I have, because of the price performance characteristics on this, is the next thing in the stack that you'll increase is the amount of natural gas, combined cycle natural gas. And that is the solution that is you're able to deploy in a reasonable time frame. With all due respect to, we're going to develop a new nuclear fuel cycle and all that sort of stuff. That's decadal, right? You can call up the good people at Siemens, GE, Mitsubishi, whoever, and you can wind up getting yourself a natural gas turbine installed in 36 months. So I think that's where you're going to have a huge economic price point. So the question is, are we going to wind up adding a cost of carbon to that to wind up driving innovation towards some of the cleaner solutions? So you can then say, we'll include the cost of storage into renewables, so you get greater economic value out of it. So I think that's what's more likely to wind up happening, rather than we're either going to all die in a Terminator-like world, or it's going to be panacea, one of the two. Somewhere in between is what's going to wind up happening.
I'm happy to chime in with what I see is a practical way forward. So a recent study that we have done, good. A recent study that we have done is that if you look at where renewable energy is getting created, about 8 to 15% of renewables are being curtailed globally today. So at the time scale that we're talking about, clean energy technologies come with different time horizon. Nuclear is going to take a number of years to matter in our power grid. And so really, like in the next 3 to 5 years, I think there's a lot of opportunity for us to figure out how to use what we have available right now. For example, how should we unlock these 8 to 15% renewable that is getting curtailed? Can we find smarter ways in terms of scheduling demand response solutions in order to use these renewable that could be utilized much better? And if we look at data center computing's perspective, that's going to require data center operator to work very closely with grid operators, for example, which I think this is a very exciting time for that to happen. On the efficiency side of things, I think there's a lot of inefficiency opportunities that computer system designers can help with. I often were asked the questions about how efficiently GPUs are used for AI model training, for AI inference. It turns out that with all the transistors that make their ways into GPUs, a significant amount of them are actually not utilized very well. There's a lot of algorithm and software optimization that can take place. And if we really do our due diligence to do that, then we can help bend the resource consumption curve of AI, for example.
So, but presumably that's only like a factor of 2 being lost there. It's not going to like, that's the inefficiency.
I think it's probably more than a factor of 2 there left. I mean, if we kind of look at the efficiency gains that we've gotten over time, and it's also not one area, right? I mean, it's a combination of lots of areas, all the way from software down to devices. But and maybe the question might be how we're talking about efficiency as well, right? I mean, if you're talking about just overhead in the data center, that may be limited what we can get. But how better to utilize the transistors that we're putting in these devices, I think there is a good bit of gain.
Yeah, I would agree. Right now we're going from, especially for a GPU, from FP 64, 32, 16, 8. Now people are looking at 2. Right? And so that's one way of just, especially it scales well for AI. And
so maybe we should explain to people who are not computer architects here. We're changing the precision of math and still getting decent machine learning
floating
outcomes.
point precision. And but there is, I think there's I kind of see it as kind of, for the energy side generation, is 2 problems. One is decarbonization of our existing energy infrastructure, right, to get it to a sustainable level. And then the other problem is, increasing it, right? And I don't see it increasing, 10x. It's very difficult, and so that's also very hard. You saw that curve; it's been very, very slow, right? It's a lot easier to make more performance than to make more power overall. But there's if you look at kind of nature in terms of compute, I don't recall the exact scale factor, but John Kelly from IBM research presented this maybe about 8 years ago or so. It was like, if you look at the compute for the human brain, the power, the energy for doing computations, is like 4 or 3 orders of magnitude lower than our computers today. So that's kind of one bar that we have, right, that we could look at in terms of computing. And that's by food, right, is generating it. Right, to do that energy, and that's what it is. It's a system. So that's one kind of asymptote. So if we get down 3 orders of magnitude, looking at different structures of how that works, and that's what drove IBM to use neuromorphic computing technologies. It didn't quite pan out yet, but they always do things about a decade too early in terms of technology development, until it's monetized, right? Which they got the right ideas, but it's not quite sustainable yet. As we come up with the large language models and everything, and figure out what's the best architecture for those, then you can start applying these other technologies that are being developed there and get much lower compute power.
Yeah, and in a lot of cases, the GPUs are a very general purpose solution, even though it's very specific, compared to CPUs, but it's a very generic compute platform for these, right? You can always do better by hard coding it. And over time, if you look at the instruction sets that we have in the GPUs and the complex instructions that we put in there, we could easily put more dedicated hardware that computes a specific network. But we're still at a point in the evolution of these AI machines and networks that you can't lock that down yet. I mean, it's changing too much. And I think that change there from the algorithm side is part of the solution, right? I mean, the way we've gotten from 32-bit to 16-bit to 8-bit to on down is not just because we changed the hardware. It's because the networks have changed along with that and been co-optimized. And I think that's where a lot of the hope is going forward.
I mean, I'm willing to cede completely. I'm an incredible techno optimist about the semiconductor industry, the chip industry, the electronics industry, the entire stack getting more and more efficient by orders of magnitude. And that's not going to solve our fundamental problem here, which is that the most productive thing one can do with electricity is use it in the information sector. The problem is the rest of society, there is nothing more stabilizing in a society than providing cost-effective electricity to elementary schools or whatever you want to wind up doing. And I think that's what we're going to come up against. There are market-based solutions we can come to wind up providing enough energy to make sure we've got enough energy for the information sector. Let supply and demand, and if the same grid only provided energy for the information sector, you'd have a price on it, you'd wind up having an effect on that, you'd wind up having new entrants into the market, and everything will be fine. The problem is you're competing between your cryptocurrency exchange with someone running electricity in an elementary school. And so the question I think the information sector is going to wind up having to face is, are you willing to live with a higher cost of electricity so that the rest of society can advance their needs for electricity? And at the point where you hit those crossover points, you're going to have to take that on as a problem of society. It's going to be ugly, but it's what we're going to wind up having to look at.
And this maybe leads into my second question here, is how or should we even try to balance the desire for generative AI with energy and sustainability goals?
Well, I would kind of chime in. Maybe generative AI is a use, but I kind of look at it. Another analogy is lighting. So we had incandescent lights forever since Thomas Edison. Up the road he invented it, and in Edison, New Jersey, and that technology has been there for 100 years, and then all of a sudden, we came with LED, because it had to be mandated, basically, which provided 10x lower energy, consumption, power consumption for the same light, amount. So that's huge. So, and if you look at generative AI, maybe we can't let it go and just unconstrained and consume all the energy. At some point, you have to come up with new algorithms, new, architectures, technologies to lower that by 10x. And I can just make 10x more power.
At the same time, sorry, go on. Yeah.
I really like the duality aspect of any important technology. I think this is a really good time to start thinking about how generative AI can be put in place to help all aspects of our life. For example, through morning conversations, I'm understanding in the audience there is a lot of experts that's taking AI for solving scientific problems. How do we accelerate material discoveries with Gen AI, for example? I think all of that is now possible because of the open source AI ecosystem. And I think this is a really great opportunity that our community and research community has to accelerate how AI can improve healthcare systems, scientific discovery, just to name a few. I think today we kind of talk about ChatGPT, large language model, but there are a lot more important use cases that we can delve into.
Solid state lighting is a great example, though, that actually supports, 20 years ago, and my research actually was doing gallium nitride crystal growth, was what I did a lot of work on for blue LEDs. And, it used to be perfectly fine to just take paint on these large signs and put them along highways to share information and advertisement. Now we have all day long in the middle of the day, high lumen emissions electricity going in to make sure we know what the price is on the Powerball or whatever it is they're advertising, right? So we actually are using almost as much electricity now as net electricity. We're doing it a heck of a lot more efficiently. We're doing it a heck of a lot more efficiently. It did, through the late 90s, early 2000s, slow down generation capacity growth in the US, but we're back on the same growth curve just because we need to light everything up in the middle of the daylight, we think. So It's going to be an interesting, I don't know a priori what the answer is going to be here. There's going to be a market driver that drives towards it. And it's technology we're going to have to deal with.
And then the negative kind of thing that keeps it down is basically price.
Yeah,
so
exactly.
If it gets too expensive to light up your sign, then you're not going to do it. Right?
Yeah.
Right.
I think it's an important point that Carol made about we're creating all this problem with the AI, but we need to use the AI back to fix a lot of the problems and to do a lot of the optimization. And there's so many things that are going on. I mean, you look at how we design chips today, how would you design systems, how we manage the data center today, all of those AI is being incorporated into that to make a huge difference. And again, this is the front end of that curve. So,
what do you all think the most promising technology is that's going to help us sort of tamp down on the energy usage of AI? Anything in particular that you had mentioned specialization?
Yeah, I mean, I think specialization over time gets there for more efficiency. I mean, using AI for design is also a big efficiency boost as well, right? I mean, to make our designs more efficient, take less time doing the designs, be able to spend more, more efficient designs quicker, and that's starting today. I mean, using large language models for as an expert, cockpit type system in our design environments today is happening. I think taking a bunch of telemetry data back in the data center and using AI to help optimize water flow, information flow, power, steering in the data centers is also an important optimization point.
Is there going to be a CMOS too?
Let's see.
Or we saw the graph that you had where sort of jump.
I think we shouldn't count that out. Right? We're moving. We're already doing gate-all-around and nanosheets and that type technology. I mean, we're on the end of that curve of CMOS, traditional CMOS, already today.
Yeah, at the end of the day, an atom is still 0.25 nanometers across, right? There's not much you can do about it.
It is true, right. But we stack them in a lot of different ways.
Yeah,
now, right?
Exactly. Yeah. So I think that AI itself will wind up getting more and more efficient. I think what's next in the stack of information technologies, quantum computing, whatever else, is going to be the next thing that follows. It's going to use even more energy. So we're always going to want to do more. So relative to this crunch, relative to energy usage, I think, like much of the renewable energy transformation, batteries. And the good news is it is still coming down, an exponential learning curve. The cost is coming down on that. And that will make it so we can actually use carbon-free electricity in these environments.
And I think there's radically different technologies. I know there is some research on things like DNA memory, right, where you can encode your storage into DNA, and using that type of technology, if it could work, in a cubic centimeter, you could store the whole written history of the Earth up to today, in a cubic centimeter. Yeah. So that's huge in terms of density, and then also, I don't know what the power, energy efficiency of that is yet, but there's technologies out there. So it'll something will happen. Right? There's a need for it.
Yeah, all of these new technologies, I think, show great promise in operational efficiency gain. I guess what I haven't heard a lot that we talk about is what is the associated manufacturing emissions that will come with each of these technology breakthrough. I guess Melody Nakagawa talked about in data center level, a significant portion of environmental implications of data center is coming from manufacturing emissions, the carbon that's embodied in our computing systems. I think that's where we don't really understand the trade-off very much. We do not have tools to quantify that very well. So how should we think about the balance between embodied and operational carbon?
So is there any promise of getting exponential embodied carbon reduction?
So in steel, I mean, the good news, because I spent a good bit of time on steel actually as well. The good news is if you don't care what your steel looks like, so you're not using it on the hood of a car, you can go to a company like CMC Steel right now and buy 98% carbon-free steel today. It's actually manufactured in a plant over in New Jersey. Fifth largest steel maker in the US, they make rebar. So putting rebar, that's solvable. Like it's all 100% scrap that they're using on it. So, but cement's a hard one.
Okay, so let's take a few minutes and open up to questions from your audience.
Chief Grassweiler, American Tower. Tom, I was looking at Hi, Jake Grassweiler, American Tower. Tom, I was looking at your chart of data center growth and energy consumption, and I'm wondering if we could break down the problem into large language models and inferencing. Because one of the trends that I see, you talked about crypto. Crypto moved to the generation source. It moved down to the oil field. And then you have AI buying 3 Mile Island and a couple of other plants in Pennsylvania. What portion of the data center capacity can move to the energy source versus need to be in a place that you have to transport the electricity to the compute, which is more the inferencing? What do you think the breakdown could be over time? Because if the grid is the constraint and a lot bypass the grid and go directly to the energy source, does that solve some of the problem?
Were you asking me or Mark here? So I'll address part of that. So inference and training are two very different things. And today, there's a lot of constraint on inference for latency in computation and latency back to the user. You type something into a large language model, the ChatGPT or whatever, you want to see something come back to you relatively quick. And so that's not there with training, and training can be done anywhere, right? I mean, it can be done wherever the power is, wherever it happens to be most efficient to do, because at the end of the day, you're converting that power into a bunch of parameters that are going to be easily shipped to wherever you want them to be shipped into the world, right? So I think that optimization of putting training where it's most efficient from a power standpoint is something that should be explored.
To add to Tom's point, training and inference are very, very different problems. On the one hand, that Tom mentioned that training can happen anywhere. But on the other hand, also is that the amount of aggregated power consumption for training data centers is way higher, whereas compared to inference can be very distributed, and it is optimizing for latency. So on the one hand, I guess we want to think about how training's overall power consumption use can be quite high, and depends on how training is being designed. It can cause a lot of significant load on the power grid itself. And also like how these GPUs are synchronized and used can also be reflected on the power grid side of things quite significantly. Whereas inference is quite distributed, and so you don't see that sort of significant power consumptions on the power grid side of things.
I think there's, I had a couple bullets saying on one of the slides, the total equivalent of for GPT-3, I think. What? Oh. Not working? Oh. Anyway, here it comes.
There we go.
Okay. For ChatGPT-3, I think the equivalent energy production or number of households for total yearly energy production to train that model, like if you made the equivalent something around, I think it was 100,000 households of a yearly energy production or consumption was equal to making that model. I think that was, as I recall it from the Bolton side. And for inference, it is lower. It's like 33,000 for daily inferences for ChatGPT. So there's a lot of users who are using it. So that's very, very high. So actually, in terms of inference, the total energy could be much higher for inference because so many people use one model, right? So you could go from. So the total, even though it takes more energy to create a model, there's a lot more people who use a model on a daily basis.
So your question was, does that solve the problem? The answer is no. So the question is, what is the problem on this. The problem is not the energy. The problem isn't the load on the grid, because we have technologies we can expand all that sort of stuff. The problem is CO2 emissions. And I don't care if you're emitting CO2 in Texas, if you're emitting it in Australia, wherever it is, we all breathe the same atmosphere, right? It's all over the entire atmosphere. So the question is, how are you minimizing it? And you're not just outsourcing your carbon emissions to somewhere else and then claiming you're clean and someone else is not. That's just a version of greenwashing that the supply chains have been doing for 30 years. So I think one of the things we need to do on it, this is boring, but it's why I put up there things like Energy Information Agency needs to pull this together. But we need stronger accounting rules kind of thing of saying, how do you determine how much CO2 so everyone is using the same terminology, the same language when they're reporting it, so that you don't have someone that says, oh, I'm not training the ChatGPT, I'm using the ChatGPT. It's that training person that actually is the one that's the CO2 emitter. And so does that count as scope 2 emissions? Does that count as scope 3 emissions? How do I count for it? I don't know. We need to come up with the rulemaking on this as part of the challenge. So it's very bureaucratic, but it's really, really important. So.
Let's take another question.
Okay. Anyhow, transmission is obviously important, and I know this administration will also run transmission. Everybody seems to be wanting more transmission. On the other hand, we know that storms, etc., and foreign countries could take out our transmission system. There's Will mentioned using AI to improve transmission. Using AI to improve transmission. Can we use AI to have alternatives to transmission, which is like microgrids, et cetera, they're just much more reliable than, in fact, a transmission system which can be taken out?
Was that for me or who is it for? So the answer is yes. And in fact, you're looking at optimizing systems anyway right now. That's important. You want to have, like any security system, you want a layered, robust solution that comes in, and you need to have a restart plan. Really, really important having a restart plan, because over a century time frame, we're going to have disruptions that happen, whether it's from some geopolitical actor, if it's a solar flare, whatever it is. There are things that wind up impacting, even on microgrids, you wind up having things knocked out. I live in South Carolina. I just spent 10 days without electricity. I don't care if I had a microgrid or not. No one had electricity around me for another 10 miles, right? So you have to do planning. It's really, really boring. It's the reason why people say, oh, why does it take so long to innovate in the energy sector? It's like they actually plan, and the reliability of your electricity is so much higher than the reliability of either your cell phone or your internet service. And it has to be, because it's the foundation for society. So the answer to your question is yes. Bringing more information technology to bear on these problems is something that people are looking at. In semiconductors, we're not even talking about power semiconductors here. There's a whole transformation with companies like DG Matrix right now that are looking at how you can use silicon carbide to build better solid-state transformers, things like that it's a revolution going on in that field as well. So all these things are coming together. We need them all.
I was on the National Academy of Science panel on grid resiliency maybe 12, 15 years ago. So I know all of that. The issue is, though, for instance, if you have in South Carolina solar and a Tesla wall, heaven forbid Tesla, but a generation backup. I know people in Puerto Rico, when they had some massive outages this past couple of years, they had little microgrids in their communities, and they came back on.
Yes.
So this country, at least on mainland, is not working in that way. It's more transmission, which I see more as a backup in the future than as the actual major source.
Yeah. So a good example of that was the ice storms that happened in Texas a few years ago. And Texas didn't share their power with the rest of the grid in the U.S., so they went down. So that was, problem.
ERCOT. They do it on their own.
So maybe I'll take one last question from the audience.
Hi, Martin Franson from Mercator Partners. My first question is for Tom. On your graph, you had vertical power. Where would you say we are today in the adoption of vertical power on the server blade?
Yeah.
That's question number one. Question number two, I saw a couple of the bios, photonics experience. So where are we on photonics? Because obviously we have a bandwidth problem coming down the pike as well. And also it could potentially help in the GPU as well at some point. So I'm interested in your views around that. And thirdly, for all of you, wafer scale chips. Isn't that also a part of, Tom, your comment on specific hardware on a chip, the lack of latency, the basically not having the memory on the wafer chip? So those three questions, really interested in your comments.
Okay. Yeah, so all of those are very important. If I remember the order here, the vertical power delivery, today's systems, there's not a lot of vertical power delivery. Almost all of the regulation and conversion is done laterally from on the board. We come in, we've just made a transition from coming into the boards at 12 volts to coming in at 48 volts. Coming in at higher voltage is less current for the same power, so it allows us to not lose as much of that current, of that power by the time you get to the chip, right? So that conversion has been done, but we still come in at 48 volts to the die. We do the conversion, then the power is routed laterally along the board. The next step for that is to actually move the converters, at least the last level of conversion, into the vertical, so you've got even less transmission distance. Sort of very similar to electricity transmission on the grid. You transmit at high voltage and you want to go as short as possible, and vertical distribution allows you to do that.
I think we're getting the hook here.
Oh, we're getting the hook. Okay. All right.
So I'll be able to answer the optical question. So optical is great if you're going long distances. You can transmit data really efficiently from an energetics perspective, but you have to transform from electrical to optical and back, and that's where you sort of use your power or use your energy, excuse me. And so it's sort of a trade-off here if you're going long distances, and we've already seen that. Long distance communications is all optics. Even medium scale stuff is optics, fiber optic communication. But as you get shorter and shorter and shorter, it may not make sense to transduce from electrical to optical back to electrical from an energetics perspective.
There's a lot of innovation there, though, going on there to push that down. And photonics overall is kind of the direction for doing that. Sorry.
We're diving deeper and deeper into technology.
Let's go to coffee.
Now you're getting the questions we can talk about, right?
So we'll have a 15-minute break and we'll come back to study policy and economics and regulation.